Yes, I left off stating that there's a lot of different events that had to happen for you to be here, many of which that science cannot give definitive answers for. So science does not have the answers for some of the fundamental questions of how the world works. Now, one of your characteristics that you have, physical characteristics, is your weight. Now, before the 16th century, no one was really sure what your weight consisted of. But Newton, back in the 1600s, he saw an apple outside of his house in an orchard fall to the ground. He said that that was an attraction between the apple and the earth. And he came up with a formula. He said it's equal to the mass, or proportional to the mass of the apple, times the mass of the earth, divided by the distance between the center of gravity of the apple and the center of gravity of the earth. The center of the earth, squared. And what is that? That's gravity. So the gravity then is the force of attraction between two objects. So you are an attractive person. When you go into a room, several people would be attracted to you. And that would be equal to their mass times your mass, the amount of material you have, divided by the distance between you and your friend, and squared. Now, unfortunately, or fortunately, that is not, you can't really measure that attraction because your mass and their mass is so small. But if you go outside, you'd be even more attractive to a mountain or to the earth itself. So you shove an instrument between you and the earth, call it a scale, and you see how much the earth is, you are attracted to the earth. And it gives you what we call your weight. So your weight is your mass times the mass of the earth times the distance between you and the center of the earth squared. So you want to lose weight then, and maybe climb a mountain, because the distance there is farther. And then when you divide by that distance, your weight should be less. If you want to gain weight, go down into a mine. So the distance there is smaller, therefore you should weigh more. Or if you want to, say, go to the North Pole, the distance there is less because the Earth is not a perfect sphere. It bulges at the equator. Then your weight at the equator would be less. Now again, it's quite insignificant because if you compare, say, the Earth to a billiard ball and the surface of the Earth to the surface of a billiard ball, you see that it's very smooth. So the difference between the top of the mountain and the bottom of the mine is very small. However, if you really want to lose weight, then go to the moon. The moon is only 1.2% of the mass of the Earth. Even with the fact that the distance between the surface of the moon and the center of the moon is much smaller, you still only weigh 1/6 as much on the moon as you do on Earth. So when you saw Neil Armstrong walking, he was almost hopping, even though he had heavy equipment on his back. And if you want to break some Olympic records, a high jump, go to the moon, because you could jump much higher there. But wait. No, he also said, Newton also said that the reason why the moon goes around the Earth and the Earth goes around the sun is because of gravity. And his second law of motion. He said that everything keeps moving unless there's something that stops it, another force. Before that, going back 2,000 years, Aristotle said no, everything comes to a stop. That's a natural thing. And of course, and to keep things moving, then you needed the hand of God. Newton said, no, take a thought experiment. Take a cannon and a cannonball up onto a mountain, drop the cannonball, and it drops to the earth, the same as the apple in the orchard drops to the earth below. But then shoot the cannonball, shoot it out of the cannon, and it will go a kilometer or a kilometer before it falls to the ground. Shoot it harder, it'll go halfway around the earth. Harder again, all the way around the earth. Harder again, it'll go around and keep on going around the earth. So it's the force of gravity then, plus the fact that things keep moving unless there's something there to stop it, and the centrifugal force that is the reason why the moon goes around the earth and the earth goes around the sun. But even there, that scientific fact is not quite correct. What happens is that in a room where you have another person, is that you're not attracted to them, or they aren't attracted to you. You fall for them. Now, for instance, women, they have fallen for every man that they've ever met, and every man that they will meet. Does that mean that they're fallen women? Well, men, even though they're not called fallen men, they fall for all females that they've ever met or ever will meet. But to be fair, they also fall for every man that they have ever met and will ever meet. And what happens there is their mass causes space around them to change. Space changes. And you fall into that space. Forms an indentation, if you like. Somewhat similar to like if you're on a trampoline, then you form a well, if you want, around you, or a bump in the trampoline, and you put a basketball on it, and it rolls towards you, falls towards you, and the closer it is, the harder it falls. So Einstein said that in 1915 that the force of gravity is not the attraction between two objects. It's a warp in space-time. What does that mean? Well, to get an idea, maybe do another thought experiment. Take a rubber sheet, stretch it out, representing space-time, and two ball bearings, one bigger than the other, one representing the bigger one representing the Earth, and the smaller one representing the Moon. Then you roll the smaller one, representing the Moon, towards the larger one representing the Earth, and it will either go right, depending on how massive the two objects are, and how fast you roll it, and excuse me, and how close it comes, the ball bearing comes to the bigger ball bearing, or the Moon comes to the Earth. It'll either go right by, it'll hit the warp that the Earth forms in space-time, and be deflected, or it'll hit the warp and go around the warp and around the Moon. Not because the Moon is attracted to the Earth, but the Earth has formed a warp in space-time, and the Moon falls into that warp and continues to go around. Now again, scientists were quite skeptical, and they should be. Science should be skeptical until you can get evidence to support it. And when evidence came, they brought back to the lab being the solar system. And during a solar eclipse, they looked at the stars behind the sun and found that they were displaced. So what had happened? The photons entered into the warp caused by the mass of the sun and were deflected. So the star appeared to be in a different position. And Einstein became then very famous. And all of the evidence supports that theory. There's no evidence that contradicts it. So it's a worldview, if you like, an Einsteinian worldview of how things work. Was he given a Nobel Prize for that? No. He was, however, given a Nobel Prize for his contribution to another world vision, that of quantum mechanics, or quantum field theory. And where he got his Nobel Prize then was on the photoelectric effect. When light hits an atom, it releases an electron. And that's why when you walk through an elevator and the door starts to close, it doesn't hit you. Or a car, when the garage door starts to close, it won't hit a car. So you can thank Einstein for that. But this other worldview is even weirder than Einstein's. I mean, Einstein's, you can go around changing space and time. And I should have mentioned that time is space and time. Why time? Because time changes as well when you approach a mass. It slows down. Don't notice it that much because we are all on the Earth, because we're all pretty well the same distance and the same warp caused by the Earth, the same distance away from the center of the Earth. However, in a satellite, which is farther away from the Earth, the center of the Earth, time there runs faster than time on Earth. What does that matter? Does it matter then? Well, yes, because if you want to use your GPS to find out where you're going, you have to incorporate the fact that time on the satellite is running faster than time on the Earth. If not, your GPS would be out in 2 hours. So the Einsteinian world then goes around and you're changing your space and time. It's not constant, like it is in the Newtonian world. Now, does this mean that Newton is wrong? Yes and no. We still use Newton's equations to put men on the moon and to fling satellites farther than they could go under their own steam by using the force of gravity of different planets to let them go farther. So for everyday use, it's often okay. But if you want to really, as I say, use your GPS, or if you want to figure out the rotation of Mercury around the sun, you'd better use Einstein's mathematics, general theory of relativity. Mercury being closer to the sun and therefore more influenced by the warp caused by the mass of the sun, you'd have to use Einstein's equations to get a more definitive answer. Time as well is isn't constant. It varies on how fast you're going. To figure that out, here's another thought experiment. You have a friend and he's going on a trip, so you say, go on a train, and when the train gets 100 miles an hour, go up the front and throw a baseball 100 miles an hour. Forget the friction, then the ball would go 200 miles an hour. And he says, wait till the train goes 3/4 the speed of light, and go up and throw it at 3/4 the speed of light. Well, how fast does the ball go then? Does it go 1.5 times the speed of light? Well, it can't. The speed of light is constant, 10 to the 10th centimeters per second. Something's got to give. The distance you go is equal to how fast you go and how long you go. D equal VT. But the velocity of speed cannot go more than the constant. So time then has to change. So the faster you go, the slower time goes. So if you want to see into the future then, take a trip in a rocket ship. And depending on how fast you go and how long you go, when you come back, you'll be seeing the future. Everything would have aged. A second, a minute, a year, a million years, depending on how close you go to the speed of light and how long you go. And at time, if you approached a very large mass, say a black hole, time would almost stand still, being so massive. And time would slow down tremendously, as we observe it from the Earth, at least. So here we have the Einsteinian world, which has you're going around changing space and time. So that's weird. And as I say, there's nothing that contradicts that. All the evidence points to that. And the other view, which Einstein didn't like, is the quantum world. One of the founders is Planck, who said that both time and space cannot be continuous. It's discontinuous. It stops at one Planck time and one Planck length. What do you call it? A quantum. So the theory is now called quantum mechanics or quantum field theory. Another founder, Heisenberg, who said, if you have two things that are related, the more certain you are of one, the less certain you will be of the other, and vice versa. For instance, if you want to know the speed and position of a particle, the more certain you are of the speed, the less certain you will be of the position, and vice versa. Not because you can't measure it, but because that's reality at the quantum world, in the quantum world. And in the quantum world, you use probabilities to really find out anything. Things are not certain, they're just probable. And you have to find what we look at as the real reality, accumulate the probabilities. So another founder who did a lot of help on quantum mechanics, and I forget his name now, but he said, anyone that says they understand quantum mechanics doesn't understand quantum mechanics. Now, to show the weirdness is the classic experiment, the double slit experiment, where you pass light through two slits, and see what happens on the other side of the projection on the wall or the screen behind it. You'd think maybe you'd get two straight lines where the light goes through the two slots. But no, you get several lines, and they're called interference lines, where the waves interfere with each other, because light can either be a wave or a particle, a photon. You hold two fingers up together and look through them, and you'll see interference lines. The same as when you throw two rocks into a pool. You'll see waves that interfere with each other. So that's why then you get to the several lines instead of just the two. But if you look at the light before it goes through, or measure it before it goes through, guess what? You only get two lines. So somehow the wave is changed back into a particle. Even weirder yet, release one photon at a time, and you think, well, there, it has to, over time, then either go to the left or the right. Can't interfere with itself, can it? But no, you get the interference lines, several. So is there something that we don't know about time? You can go through two things at the same time, or what's happening there? That's very weird. And if you observe the one photon at a time, then yeah, you get two lines. They end up along two lines. So does that mean, and here again you can get, if you want to get a religious connotation, that doesn't mean that something is there in order to change waves into something or someone is observing in order to make all the material change from a wave into a particle. Now, as I say, it's a very weird thing, and so Einstein didn't like the quantum mechanics, that world vision. Yeah, he said God does not play dice. And he spent the most of his career, end of his career, trying to combine the two to get a theory of everything. In quantum mechanics, the mass is so small and the force of gravity is so weak that you can pretty well ignore the force of gravity, whereas you can't, of course, in the Einsteinian. And so you can still use your quantum field theory to predict, and it's more accurate than any other tool that science has, predict things to 23 decimal places, for instance. The only time you're going to run into problems if you have something small and massive, like the beginning of the universe, or like a black hole. And many scientists have tried to get a theory of everything. Some have had some luck, if you want to call it that, but only as a hypothesis, saying that everything is composed of strings, much, much smaller than quarks, even forces. But the only problem is you need to have 10 dimensions instead of our normal 3 spatial dimensions. And as far as I know, no one has created another dimension and come back to talk about it. So it's all very still on hypotheses. It's not really a true theory, if you want to call it that. So we have two world visions. Science doesn't know. Can't explain. Why are there two different visions of how the world works, how everything works? And yet they both are have evidence to support both. So you can call both theories, and yet they're incompatible. Einsteinian is certain, and the quantum field theory is not certain. In quantum field theory, they're saying everything starts as a wave, and then is converted into matter. Einstein's the quantum world is built on probabilities, and nothing is certain until you aggregate the probabilities to get something that we would think of being close to reality. And Einstein thought, he said, only when you could combine these two world theories, then maybe then you'd be closer to knowing the mind of God. Now, the other thing that science cannot really explain on a fundamental basis is why all the different forces and all the different constants are exactly the way they are. Because if they were slightly changed, you wouldn't be here, nor the universe. For instance, if the force of gravity was any weaker, then when all that hydrogen was produced, it couldn't have brought that all together to eventually form stars and the rest of the universe. Or if it was any stronger, once the hydrogen was created, it would have drawn it back, attracted it back together into a big crunch. And again, nothing. You wouldn't have the universe or you. The other constant that it can't understand at all is the cosmological constant. Einstein put it in his equation, and then he took it out. It was lambda, and it's because it explains how the universe can expand or contract. And he thought, like everybody else, well, this doesn't happen. It's just there, which he called the biggest mistake in his career. Biggest mistake was thinking that it was a mistake that was in there, because he now needed to explain the expansion of the universe. So they looked at the expansion, figured as the time goes on, it's going to slow down, get cooler, slow down, and eventually maybe turn around and go back into a big crunch when the gravity takes over and pulls everything back. Much to their surprise, they found it was not slowing down, it was actually accelerating. So there must have been something contradicting or something opposing gravity, trying to bring things back. There was energy trying to fly everything apart. They call it dark energy, not knowing what it was. Speculate that space itself is not empty. It's full of virtual particles and virtual antiparticles. Very hard to test that out, because if it's virtual, it isn't real. But that might explain, and again, it's a hypothesis because you can't test it, why as the space expands, you get more virtual and anti-virtual particles, and hence more dark energy. So that causes the universe to expand, because your matter, which is responsible for your gravity, stays the same. So dark energy is winning over gravity, force of gravity, and the universe is expanding. And it needs to be 75% of the universe then, in order for the prediction. They also realize that the amount of matter in the universe isn't enough. It needed 4 times as much to explain some phenomena. And this dark matter, then this gravity is needed, or all the matter is needed to form the gravity. And it's not like the normal matter. It doesn't have quarks, atoms, molecules, chemicals. And it cannot even be seen with your eye or with an X-ray, any of the electromagnetic spectrum. It's a complete mystery, and it's so we call it dark matter. And that consists, they need that 20% of the universe. The reason why they figure they need that extra dark matter to explain how the stars, outside stars in a solar system, and in a galaxy, go around the center of the galaxy. The center of the galaxy most likely being a black hole. So when a skater spins and puts his arms out, he slows down. When he brings his arms in, he speeds up, spins faster. Well, it's the same that happens, in a solar system. The farther out you go, the planets go, the slower they go. And that should also happen then with the stars going around the center of the galaxy. But it doesn't. You need, as I say, more gravity. 4 or 5 times the amount of gravity to explain. So here we have science. It's in the dark for 95% of what's happening in the world. And the other 5%, it doesn't know either. It has two different contradicting theories. Call them both theories because they both have evidence to support them. So when you think science has the answer to everything, no, it doesn't even have the fundamental answer to how everything works. The other thing that science cannot quite explain is why did we get all these laws, all these theories, all these mathematics, equations from the universe, from reality? Before 1905, then these all changed as well. But before 1905, you had Newton's law of gravity, Newton's law of motion, law of conservation of energy, law of conservation of matter, Boyle's law, Charles' law, so on. And many of those laws changed after 1905. Became replaced by Einstein's general theory of relativity and his special theory of relativity. And all of the math that comes from quantum mechanics and quantum field theory. So what if it's the other way around? We don't derive all those laws and he cut them all out from reality or from the universe. We create the universe and create the reality from the mind or from the math or from the laws. We all know that we can create virtual reality now. Have performers that have died, they're on stage doing a performance from the past, using holograms, virtual reality. The only problem, I guess, is should you clap when they're finished because they're dead. Now, you'd probably, if you wanted to create the whole universe, of course, you'd have to have something a little more powerful, maybe something omnipotent, or somebody a lot smarter too, probably omniscient, and something that happens everywhere, omnipresent. And these are definitions, of course, of God. So maybe science points to the need for the spiritual, rather than trying to contradict it. It points towards So you might even want to say that the two are compatible. And when we find something that we don't understand, or we think we may never understand, we say, God already knows. And when we find something that something that's fortuitous, that happens, or something that could be a disaster if it happens, we say, thank God that happened. Or thank God that it doesn't happen. So you could say, thank God there's a force of gravity to keep you grounded and keep the Chinese from falling off the earth. And thank God the electromagnetic force is greater than the force of gravity. Yes! Sorry for that interruption. Yes, if the force of electromagnetic force is greater than the force of gravity, otherwise you'd fall right through the earth, like with everything else, into maybe a black hole or a singularity. And God already knows what that is. And thank God the strong force is greater than the electromagnetic force. Otherwise you'd fly apart. You and your atoms and everybody else, you would fly apart at the seams. Thank God there's a weak force. Otherwise you'd be bombarded by solar and cosmic radiation and wouldn't have an atmosphere that you can breathe and protect you from a lot of the debris coming down from space. And thank God all the different events that happened, that without them you wouldn't be here. Many of which science cannot definitively understand. So whether you think that you are here because of random fortuitous accidents, or you really can thank God, who's there looking after you, changing your waves into matter, it's still miraculous that you're here. And is science and religion compatible? Well, on a fundamental basis, yes. The one almost needs the other. And so as long as you keep the science in its own realm, the physical, and the religious in its realm, the spiritual, then you can say that they are compatible. End of story.